Ладно, давайте тогда начнем. Я хотел сделать несколько комментариев по поводу, во-первых, гомологии. Да, я, наверное, по-английски буду все-таки читать, потому что у нас есть английский слушатель. So I want to make some remarks on homology, because we have paid more attention to cohomology, because it is related with some extensions of groups, so geometrically it is some kind more important. However, for class field theory we also shall need homology, so let me do some additional remarks. Yeah, so first of all, notice that of course if you have inclusion of the groups, so you have corresponding map between group algebras, or even if you have any map between groups, you have map between group algebras. In particular, you can apply this to H equal to trivial group consists of one element. So this is just the second. The target is just C. Yeah? So you can put this. So here you may put Z, and here you may put the kernel. And clearly, so the kernel is ideal, and clearly, so the element G maps to just per unit, and the corresponding representative. So the linear combination here of G with integer elements maps to the sum, of Mg. And Ig can be, so you can describe the generators. Yeah, so the generators is generated as ideal. So this is homomorphism of algebra. So this is two-sided ideal. So this is two-sided. And it is generated by the elements of the form G minus 1. Yeah? So for any G that belongs to G. Yeah, so that means that you are allowed to multiply this from the left side. So actually this can be also viewed as the ideal generated by any difference of two elements, but this set of generators is of course enough. So why we need this ideal? Yeah, because recently we have considered covariance, so Mg. That was just the M factored by so M was a module with so M is the G module. So you just take a quotient via the submodule generated by this kind of elements for all elements of G and inside the group and M inside M. And you can view precisely that. So that G M minus M is just application. So you can view this like writing down G minus 1 applied to M. And this is nothing, if you look at what is this ideal, it is just ideal that you can write via this ideal, just that appear in the evaluation map. So this is just Ig times M, so that means that this is submodule of M, so generated by the products of the elements from Eg and M. Yeah. So this allows you to write down the function of covariance. Yeah, so just think that you just factor this by Eg times M. And moreover, you can also apply something to this exact sequence. So also you may think of, so you have this exact sequence. And naturally, everybody has a structure of G modules here. So you can apply a long exact sequence of homology. Apply long exact sequence of homology. Yeah, so here, of course, Z has trivial G action. Yeah, so that trivial G action. Here it is a quite interesting moment that, and so from the Z has the module with a trivial G action can have a non-trivial cohomology. Yeah? So and the module that the problem is that it is just not free from the viewpoint of module of G module or ZG module. So ZG itself has trivial cohomology, and so you may write down writing down of the exact sequence. So writing down EG, yeah. So like it maps to HI G ZG. It maps to HI G Z. And then when we are considering homology, yeah, so the index is decreased. Yeah, so that you are considering HI minus 1 G IG. And yeah, so again, this is I minus 1 Z ZG. Yeah? So here you see that ZG is free. So ZG is a free module. So that means that this homology and this homology vanish. So you have isomorphisms here. And here it is quite convenient to apply this when h is equal to 1. Yeah. So let us apply this when I is equal to 1. Yeah. We have, yeah, so yeah, one should write down this explicitly as proposition. So just proposition that HI G is equal to H I minus 1 G I G. And of course one can ask why to reduce the so Z has the most trivial structure, so why should we reduce homology of Z. Why we should calculate it via homology of much complicated module? But here one can see that if, for example, I is equal to 1, then this is precisely a calculation of this homology group, because here you have H0. So this is just taking coinvariance, and you may write down it in terms of the ideal is EG. Yes, so taking into account then mg is just m modulo IgM. Yes, so you get that this is just Ig modulo Ig square. Why this ideal is important for us? Yeah, because you have the ideal Ig is ideal of the group algebra. Yeah? So claim that actually I shall give you several problems. So this will be the part of the exercise sheet. So here you can map G to Ig, of course. How? Simply. So this is just a map. Yes, so this you can map just G to 1 minus G. Yes, so just trivial. But notice that if you map to G to G modulo Ig square, so this will be a homomorphism of groups. Homomorphism. Yeah, so notice that. Yeah, so notice that this is. Yeah, so here you should be cautious about the structures. Yes, so on G, of course, you have. So here you are making multiplicative structure, and here, of course, due to the fact that G minus 1 times H minus 1 is equal to 0. Yeah, so because this is an element of Ig square. Yeah, so you have relation GH plus G plus H plus 1 equal to 0. Yeah, so you can sorry, here you have minus. Yeah, so GH minus H minus G, yeah, plus 1. So you may see that you may subtract GH minus 1 and plus 1 minus GH, and write it down plus 1 minus G equal to 0. Yeah? So you see that this is, so here you have, GH maps to the sum of HG. Yeah? So, to somehow to the sum of 1 minus H and 1 minus G. So this means that this here you are looking at additive structure, and here you are looking at multiplicative structure. And also, so one can notice that you can consider, so that will be exercise, and that will be also in the home exercise sheet. So this map factors through. So the commutant maps to 0, and this map, so of 5 commutant is equal to 0 in Ig modulo Ig square. So you get the homomorphism from the abelian group to, so precisely to Ig square, and one can check that this is actually isomorphism. Yeah, so also exercise to check, so prove that it is isomorphism. yeah, so one can do this somehow by formulas, or you can think of universal property, so that Gmod the commutant has a universal property that any map to Billion group factors through this kind of group. So this is not what you have to do is to check the corresponding universal property, for example, for EG modular EG square. So this is not too hard problem and quite interesting. Yeah, so also I want to have some remarks on chains. Remark on chains. Да.
Фи действует.
Фи просто отправляет очень просто. Ну, G, да, элемент, он отправляет в G-1. Ну, то есть, как бы у вас это, да, и G называется аугментационный идеал. Ну, как бы вот стандартное название, потому что вот это гомоморфизм аугментация, да, то есть все элементы отправляются в единицу. И вот, ну, видно, что, ну, как бы вы должны отправиться как-то в ИЖ, ну, вот это тут и написано. И поэтому я вот это и проверял. Здесь, да, их как бы произведение это просто элемент из квадрата. Я раскрыл скобки и перекинул, ну, то есть увидел, что элемент GH переходит в 1 минус GH, и он равен сумме. То есть как бы мультипликативный закон переходит тут в аддитивный. И на самом деле, вот почему это отображение важно, потому что это вот и есть будет, ну как бы вот и почему мы будем говорить о законе взаимности, ну или там как бы вот сама теория полей классов, почему она связана именно с абелевыми расширениями, то есть теми, для которых группа была абелева. Вот на самом деле в том числе вот из вот этого места. Потому что вот то отображение, которое мы собираемся построить, это будет гомологическое или когомологическое отображение, и вот как бы, но оно будет из первых гомологий, из-за этого у нас из первых гомологий, и которые вот как раз отождествляются ну, с ИЖ, ну, либо с коммутантом, либо ИЖ фактором. Yeah, so the other, so remark on chains. Yeah, so you may think of just, notice that just also we have we can calculate the covariance via the following. We are just mapping, taking the Z with trivial action, taking group algebra and tensoring the module over the group algebra. Yeah? So the idea is to change Z for projective resolution. Yeah, that we have written, yeah, so that we have written it in terms of so ZG square, and etc. So you can, and also you may think of this. Whenever you are taking tensor product, yeah, so you are just taking the guys which looks like ZI, and the tensor product is over ZG. This can be viewed as the maps from the several copies of G. So from several copies of G to M. And yeah, just because of course, this, yeah, so this is via, this is via identification, because you can, so for ZG you can identify trivially with its dual, yeah, because this is Freezy module, so you can think of that you are identifying this with the set of functions on the group. So you may map this guy to M, and but the only thing that what is about these maps, yes, so you when you are taking the tensor products, yes, so that means that in tensor products you have only finite number of summates. So the condition is that this map is non-trivial. A map is non-trivial only on a finite number of elements. Non-trivial on the finite number of elements. Yeah, so then you have the condition of, so notice that you have ZG and ZG acts diagonally here. Yeah, so this is not just free module, it is, so this can be viewed as some kind of ZG equivalent map. And the exercise is to write down the differential for this complex. So exercise, write down, right. Differential. I shall give you the answer for non-homogeneous cochains. That means that this condition, yeah, of commuting by multiplication of ZG and with M, yeah, so that you can rewrite it. So these elements, you can think of the tensor product simply thinking of the polylinear maps, yeah. So just and you can write differential for this non-homogeneous cochain. So I shall give you the formula for this differential. What you have to get that if you have x so x the map from G so Q elements, yeah, so you are writing down differential, and this is homological differential, so it has a smaller number of entries than Q, yeah, so Q minus 1 entries. And this is just can be rewritten as G that belongs to G, G inverse of X, G, G1. Yeah, so sorry, here I'm writing down differential for homogeneous cochains, yeah, because you can just no, on non-homogeneous. Yeah, so the target is the module with the structure of G, but the cochain is not homogeneous, meaning that for homogeneous cochain you have the multiplication of all entries by G results in the multiplication of the target. Here the answer is different. Yeah, so this is just an application of. So here you should do the substitution that we have done for cohomology. In order to get the answer for non-homogeneous cochains. G inverse, G plus 1, etc., G Q minus 1. Yeah, so you are just putting G to Gj, you are writing down G inverse in the next entries, and then you start with writing down G plus 1. And the last term is just minus 1 in the power Q. G is G1, G2, etc. G minus 1G. And you may do, of course, you may do the following. Here you may calculate this for one chain and get our answer. Yes, so just calculate H1, yeah, that ZG, which is G modular commutant, using this cochains. Yeah, so using formula for cochains. For chains.
Можно еще раз формулу, что там написано во втором слагаемом?
Ну, мы спрашиваем, ну, как бы, вот у нас есть вот цель, да. Ну,
да, просто что во втором слагаемом написано?
Да, во втором слагаемом написано, ну, x примененное к g1, g умноженное на g, дальше идет g в минус 1, ну, в следующем аргументе, дальше g плюс 1 и так далее до g q минус 1.
Сейчас, то есть у нас...
Сумма по всем g, да.
Сейчас g умножается на g.
Ну, да, давайте еще, ну,
да,
давайте напишу, вот. У вас есть g минус 1, дальше следующее это g на g, да, g-то умножается на g, дальше вы ставите g в минус 1, но вам нужно добавить еще один аргумент, вот вы так и добавляете g к одному из множителя g минус 1 к другому. И вот последний, сейчас, последний как раз, то есть вы вот этот g плюс 1 не теряете, ну вот g плюс 1 и так далее, g q минус 1. То есть вы в одном месте к g приписываете g и вставляете в следующее свободное место между ними g в минус 1. Ну просто. Вот. То есть смотрите, как бы у цепи q аргументов, вот как бы и нужно как-то использовать вот этот лишний аргумент, и он убирается за счет суммирования. Ну, то есть, когда мы смотрим к цепи, мы просто выбрасываем аргумент, когда мы переходим к цепям, мы наоборот используем этот аргумент посредством суммирования. Вот. Это, ну, что касается гомологии. Вот, соответственно, ну, вот, давайте теперь перейдем к... Да, ну вот нужно поговорить еще о лемме Шапира и, соответственно, ну, как бы следующим этапом будет переход к гомологиям Тейта. Я объясню, что это такое и зачем они нужны. Вот, ну давайте напишу. Yeah, so let us write down Shapira's lemma. Yeah, so this is just comparison of two functors. Yeah, so so let us recall that you have co-induced module. That is written just home ZGA, and then you have if you can just co-induced module is constructed just via the Frey-Abelian group. Yeah, so that lambda is Frey-Abelian group. And or just just not necessarily free. You can think of you can think of the module etymologically. You can think of a Abelian group, and you can embed A into this form of ZGM, ZGA. Yeah, so here we forget the structure. So in order to say what is the structure of the G module on Holmes, yes, so you have to, so there are many different ways because you have many actions. There are several different ways to introduce the G action, but here you just introduce the action by saying that you are applying, if you want to act G on phi, this is just the action from the right. Yeah. So G tilde G. Yeah. So in order to get this well-defined action, so we do not take into account any possible action on lambda. Yeah. So then you can embed A into this module just by forgetting action on G action on A. And if so, similarly, we can do the same trick. Yeah, so we have denoted this like yeah. So this yeah. So just yeah. So we can also introduce the same thing when you have the following situation. So consider the group and the subgroup, and then you can start with H module. B is H module. So here you think of this as a lambda was, for example, a trivial module, the module of a trivial group. Yeah, so that this construction is just saying G that contains the group generated by just the unit element. So lambda has a trivial action. And so you can consider H module and associate to it the following module, which is from the over ZH, ZG maps to A. So this yeah. So then you can consider yeah. So let us denote it by B with star. I mean, there is no meaning that it is dual. Just denote it like this. Yeah. So yeah, and of course here you have the action that we defined similarly. If you want to if you want to take phi, so we want to consider G action on this set of Holmes. So phi maps to G phi.
А все еще Абелева.
Ой, это B, извините. Ну, H модуль, да, вот сюда ставите H модуль. Ну, чтобы как бы ZH действовало тривиально. And the action of G here is just saying that G phi applied to G tilde is just equal to phi applied to G tilde G. So then, of course, here you can do the following thing. Here you can consider two functors. Yeah, so here you can, from B, you can take H invariance. So you can take BH. And here you have G module, yeah, so you can take G invariance. Yeah, so just. Yeah, so you are taking G invariants here, and the claim is that so of course B maps to this kind of thing, and this you can so the claim is that this is just isomorphism. So the functions are just the same, and what are these maps? So this is just actually you can put the maps in the both directions. Yes, so if you have the map phi, yes, so you can map to phi 1. Yes, so you have unit in the group algebra, so you can map phi to phi 1, and by the element of BH you have also. So if you take G invariant, then let me write down what means G invariant. So if phi is G invariant map, then you get that G phi of S is equal to phi of SG and equal to phi of S, because this is precisely G invariant. But if you are thinking of just of H, so that just restriction to H, this gives you the map from H to B, yeah? And but phi of you have equivalence, so phi of E is equal to phi of H. This is just saying that you are this is here you have H times phi of E. This is equivalence with respect to H. Equivalence. So this is by definition that you are taking home. Yeah, so that we are taking home from the H from the G to B. Yeah, you are saying that when you are taking this home, you are saying that you can commute the argument with the elements of H. Yeah? So you can, if you are taking phi from the elements of H, you can take any element of H out of phi. Yeah. So this is just saying this part is just saying that you are in the home, and this is this part is just G invariance. Yeah. So this is G invariance of the map, because this is right action, yeah, of map, and this implies that simply phi of E is this implies that phi of E is just belong to BH invariant. So similarly, you can give the corresponding construction, and the vice versa map. And that maps to invariant, to invariant you can associate this kind of homes. You just take you just say that G is mapped. Yeah, so you know that phi of SG is just phi of S. You just map have a constant map to H invariance. Yeah. So this allows to identify functors, and in order to identify cohomology, you can, for example, use either. So you may see that, for example, via the visage, so proof of Shapiro lemma, proof via the visage. By noticing that you can always map B into the co-induced module, and you may see, yes, so the following diagram is commutative. So just H of H B. So you have a map from G to. So the restriction map to H. So the G cochain can be restricted to H cochain, and here this is boundary homomorphism, which is so that means that B was H module. So that means that Hi of H B tilde is equal to 0 for any I. B tilde is co-induced. So here you have first the homology of the quotient, and here with the shift of here we have isomorphism by induction. The only thing that you have to, in order to apply induction, here you have to notice that so here you have delta, but here you should also notice that if you consider the corresponding module for G, so you have to take the induced module of B tilde mod B, which is it's a small exercise. That it is just equal to G B tilde star B star. And what you have to do is to understand that B tilde, in order to say that this is isomorphism, to say that it is isomorphism, we have to establish that B tilde is also co-induced. B tilde star is also co-induced for G. So because only in this case we can write down long exact sequence and say that both sides are vanished. So you have here on the right and on the left hand side cohomologies of this B tilde star. But if it wasn't co-induced, it won't be clear that this cohomology vanished. But this is true. So this is just this is the easy direct calculation. So that if you took B tilde as just home, let us recall that B tilde is home from ZH lambda. This is just a base change. So that we are looking at B tilde star. this is home from ZH, ZG, home to be tilde. And this is nothing as just home from Z, from ZG to lambda. Yeah? So that the shift is consistent with this kind of thing. And also, yes, so you can think of, for example, and important example of application of Shapiro's lemma. Yes, so you can consider. So now we can consider Galois cohomology. So or you can say explicitly what is Galois cohomology. Just saying explicitly say what is the group and what is the corresponding module. And example of application of Shapiro lemma.
Можно вопрос?
Да.
Там установили симметризм факторов, просто исходных.
Да.
Из этого автоматически не следовало, что сама lemma Шапира. Просто потому что...
Ну, следовало, да. Но я просто хотел вот эту согласованность еще отметить. Но, то есть, конечно, я просто, только вот, то есть это рассказываю только, чтобы видеть, что вот это вот все со сдвигами хорошо себя ведет. Просто дело в том, что когомология групп, они вот благодаря вот этим сдвигам становятся лучше, чем обычная когомология. Мы сейчас увидим это на когомологиях Тейта. Это, я бы сказал, вот это скорее иллюстрация. Да, конечно, мы берем из матрицы функторов. So, the example of applications of Shapiro's lemma. Ну и там то, что я говорил тоже про диакоциклы, я там, то, что вы немножко пропустили, там тоже я много чего излишнего говорил, просто есть разные определения, их полезно между собой сравнивать. Конечно, если мы стартуем с более общего, удобно пользоваться как производными функторами, а не цепями, но иногда нужно написать какие-то формулы, вот тогда и нужны эти коцепи. То есть, если все-таки мы хотим в результате получить все-таки явную формулу, тогда нужно что-то написать на уровне КЦП. Или, например, когда мы хотим написать первые когомологии или там первые гомологии, иногда это просто полезно. Например, просто благодаря этому можно их как-то обобщить на, например, неабелев случай. Об этом мы тоже немножко поговорим. So you have example of application of Shapiro's lemma. So suppose that L over K is the field extension, so Galois field extension. Yeah, so you have Galois group is equal to G. And you may think of, so you may consider different, so for example, you can take L, you can consider as a G module. Yeah, so consider as G module. And also actually you may take the group of multiplicative elements, and also we can consider L star L without 0 as a G module, so it is just L without 0 element multiplicative group. So this you can consider them as G module, and you can ask what are cohomology of this module. Yeah? So you can ask what are HI of G for L. And now we recall the famous theorem that is called normal basis theorem. So normal basis theorem. Yeah, so actually we shall, while recalling it as a theorem, we shall use it to derive that higher cohomology vanish actually the claim is that this cohomology vanish. Yeah, so for I is bigger than 0. Yes, so for I is equal to 0, you have to take just to take invariants, and the invariants are just the subfield K. Yeah? So this is so trivial H0 of GL is just the initial field K. And but then we shall introduce non-abelian. After non-abelian cohomology, first non-abelian cohomology, that will and we will prove that it is trivial. That will allow us to prove normal basis theorem. And normal basis theorem tells you that so if you have an element x of L, yeah, so you may consider the orbit by Galois group sigma x, where x runs through, where sigma runs through all elements of group, and you may ask, so you may take a linear span over K, yeah, so that take a linear span of these elements. Take linear span over K. And the claim is that these elements are just generate the whole field L. You have similar picture, for example, if you have this is primitive element theorem. So if you take sufficiently general element in the separable extension, yeah, so then we see that its powers generate the whole space. Yeah, so this is primitive element theorem, and this is the same thing, but instead of operation of powers, you are just applying the element of Galois group.
В чем теорема состоит? Что просто дает L?
Да, это просто дает L, и вот они линейно независимые. То есть вот как бы L получается как сигма от x, ну, линейная комбинация. Причем, ну вот все вот эти вот сигма от x, они получается, ну, то есть они линейно независимы.
Это существует такой x?
Да, существует такой x. Ну и понятно, что он просто достаточно общий. То есть, ну как бы, если мы можем говорить, ну если у нас неконечные поля, да, мы можем говорить об общности элемента, поэтому это просто достаточно общий элемент. Но на самом деле, как бы для конечных полей эта теорема доказывается отдельно, а для, ну как вариант, а для, для других она, для бесконечных, вот, ну, как бы ищется достаточно общий элемент. So all sigma x are linearly independent. So that means that the stabilizer of the element in the Galois group is trivial, and this allows us to say that the group of this is precisely the following, that L is equal to the group algebra of G applied to your given element X. Yeah, so you are fixing element. And up to so generate kx, the field, and then you are applying the whole Galois group. And this is just saying that this means that L is induced from the K module. So L is induced from K module Kx. And this implies that if you want to calculate the homology of L, cohomology of L, it is nothing as taking the cohomology of the induced module. Yeah, so up to Kfx, and this is nothing else as the cohomology of the trivial group with in the field Kx, and that is 0 for I bigger than 0.
And here we use that induction and co-induction coincide.
Yeah. For finite groups, the induction and co-induction coincide. Yeah, so we just pass it the door. Yeah. So then the next topic is Tate. So this is all for a moment about Shapiro's lemma. Now I want to discuss Tate cohomology. Yeah. So the thing is that so the starting point that Tate cohomology yeah, so the starting point is the following. So you and some kind of motivation that in topology, for example, so you have when you consider homology and cohomology, for example, you can do the following. If you have two cocycles, you can multiply them. Yeah? So in order to get the larger the cocycle and the higher degree, if you have a cocycle and the chain, you can that depends on the length of cocycle and the chain. So if cocycle is longer, you can substitute the chain in the cocycles. If cocycle is shorter, then somehow you are thinking of a partial contraction of the chain with this cocycle, and you get the chain as the result. So you have many different products that you are allowed to take the pairings between homology and cohomology. And in the same time, yeah, so this for group homology, you cannot, for group homology, you cannot compare, so you can also compare the covariance and invariance. So let us consider the following map. So A is G module. So assume that G is finite. Then we have considered. So we have considered also the corresponding theory for a finite index. Yes, so for subgroups of finite index. But here we shall need only the map from A to the invariance by mapping element M to the sum of G times M. So where G runs through all elements of G. Of course, so here I do not divide by the corresponding the number of elements. And but notice that this map can be factored. So notice that since if you apply such things to so the operator, the averaging operator, you can apply to d tilde minus 1 m. Yes, so the element of this form. This is just the same thing. Yes, so this is averaging over G and G tilde. So this is just equal to the averaging over G. And minus the averaging over G. So this is just 0, yeah? So this is, this is just 0. So you see that our operator, and so it norm operator, it acts trivially on the kernel of, so, and here you have, so G minus 1m is so the just the module that is generated. So in order to write down covariance, you are taking m and factorizing it by the submodule generated by G minus 1 times m, and you see that this norm map is trivial on this submodule. Yeah, so that means that just n is trivial on the elements of this form. So this means that n factors through coinvariance. And notice that also you can
Тобто мені А-фактор впав.
а?
Там є А-фактор впав вже.
Не, просто АЖ снизу. Ну, в смысле, это, ну, это есть коинвариант. Ну, в смысле, это обозначение, конечно. То есть, ну, мы на факторе нули, поэтому это мы вот так протаскиваемся. И, but notice that if you multiply by notice that also here you have elements. Yeah, so this map is not surjective. So map is not surjective. And not injective in general. So this so instead of writing down these guys, you have a kernel, and so here you have this norm map, and here you have kernel and kernel of this maps. So that you have kernel of M. And co-kernel. Notice also here that if you, for example, if you allow to divide, yeah, so that you see that the norm map will be surjective, yeah, because it will be surjective on AG, yeah, so that if you start when allowed to divide by G. This means that by the order of G. Yes, so that means that you can map invariance. So you, in the subset, and when you apply norm map and you are dividing by G, then you have isomorphism. Yes, so the invariant maps to itself. Yeah? So it is not multiplied by G. So notice that, yes, so this tells you that kernel and co-kernel are actually torsion modules. Yeah, so that torsion modules via multiplication by G. Yeah? Yeah, so the co-kernels torsion. Yeah. So this yeah. So then the next idea is try to do the following. So now you have yeah. So you are comparing the module. Yeah. So you are taking. You are thinking of the module, and you are having the cohomological sequence and homological sequence, and the zero derived functor, one is just this one, and one is this one, and between them you have a pairing, the map. So the idea is try to connect, for example, long exact sequence into the just you can connect long exact sequence for homology and cohomology. So, for example, you can write the sequence of modules. And you can write exact sequence for homology and cohomology. So you have here you have H1 of C. It maps to H0 of GA. So H0 of GB. So these are just taking coinvariants. H0 GC. And you have corresponding so H0 of GA, H0 of GB. Yeah, sorry, homological functor taking invariance. Yeah, the target is invariance. H0 and GC and H1 GA. So etc. And yeah, so here you have the corresponding norm maps of A, norm map applied to B, and norm map applied to C. Yeah? And here you can think of, so here you have a kernel of NC, and you have the corresponding co-kernel here. Yeah? So for A. And of course, yes, so you can do the following. So you can apply you can apply snake lemma. Yeah. So you can take this kernel. Yeah, so you can lift it here. Look at the element, etc. Yeah. So it will be element. So since it maps to zero, so it will be differential of the element here that you can map to co-kernel. So this is by snake lemma. You have a map between a kernel of NC to co-kernel. Yeah? So by snake lemma. You have the map from kernel of NC to co-kernel. And the idea is just to change the zeros homology and zeros cohomology in order to have, so here you see that this long exact sequence doesn't match, so you have a part from the left hand side and a part from the right hand side, and you have a map between these guys. But the idea is so that why we want to use why we want to postulate homology is to write down the long exact sequence for a larger complex. Yes, so that you are writing down H of so here GC, and you change this by groups H0 So by homological zero groups, GA homological zero groups GB, homological zero groups GC, and then you pass to cohomology via this norm map. Yeah, so you want to induce this by this delta map that we have introduced, that map from kernel to kernel. Yeah, so you just are thinking of this delta map from GA to H0 GB, H0 GC, and then you map to H1 of GA, etc. So you are changing your complex slightly at this the initial. So changing the invariance and co-invariance by the different functors in order that we are just on previous step where we are thinking of taking resolution that such that the functor of taking invariance is derived functor, so you can calculate it via resolution, and the co-invariance you can calculate it with another resolution. And here we are just taking this resolution, and via the norm map we are matching them together, and we change of course the zeros, and you are just taking the one resolution, taking the other, and take the map between them. This will do the change in two entries, zeros and zeros homology and zeros cohomology. And then we introduce state cohomology just to match the resolutions. Yeah, so you may think of this as saying that between your so you are taking resolution of M, just project one P0, P minus 1, P minus 2, and just M maps to by the norm map. The norm map is still valid on. Then you are taking, well, that we can call injective resolution. However, in this setting it is also generated by free module. So, and then you are just reorganizing this in order to get rid of M. Yeah, so that you map from P0 to I0. Yeah, so by changing kernels and free kernels. Yeah, so I'll let you do it after the break. Okay? Я немножко устаю сегодня. Да, я просто посижу.
проективная кривая,
Да,
связанная, но не обязательно гладкая.
да.
И мы знаем, что h1 от OC это 0.
Ага.
Из этого следует, что это кривая P1. То есть как это? Арифметический род, наверное?
Да, да, да. Ну, следовательно.
То есть
Ну,
я
просто надо через особенности. Ну, как бы нужно написать формулу через особенности их кратности. Да? То есть, ну, как бы подумать, что кривая там вложена куда-то.
Да.
Ну, вот, и попробуйте просто раздуть. Ну, то есть, просто особенности можно разрешать с помощью раздутия. Или, может быть, наверное, можно проще сделать. Ну, вот, нужно написать морфизм нормализация. И вот как-то, ну, написать вот, ну, типа того, что, ну, а там тоже в Хартсворне, если откроете, там есть вот, в том месте, где есть морфизм нормализация, вы берете один, ну, пучок от x, он отображается в нормализацию, есть фактор пучок. Ну, фактор пучок, он сосредоточен как раз в множестве особенностей.
Да.
Ну, это прям наборы точек, поэтому как бы вот вы их можете когда с ними работать, написать H1 от этого. Ну, H1, ну, написать длинную точную последовательность, как мало. Ну, там появится H0 и H1, да, ну, к чему это приведет, что у вас есть H0, ну, в самом начале. Ну, как бы H0 будет от набора точек, он отобразится. Ну, у вас U от x, V от x нормализация отправляется. Фактор это пучок, сосредоточенный в наборе точек. Значит, у вас H0 от пучка в наборе точек отправляется в H0, в H1 от x и в H1 от нормализации.
Да.
А дальше H2 уже. Ну, в смысле,
Нет,
дальше
дальше
H1 от набора
Да.
точек, он нулевой. Да. Вот. А дальше H2, ну, какой-то.
Ну хорошо, то есть. Ну да, то есть нормализация рост получается может только.
Ну, получается подскакивать.
Да. Нет. Наоборот, уменьшаться. Вот вместе.
Да, меньше.
А уменьшаться ему некуда, значит и точка.
Да.
Нет, они могут в ноль, правда?
Не, ну H0 от точек всегда не, ну, то есть,
Не, ну а при этом граничном отображении.
ну, не надо, ну, в смысле, вот там не надо. Ну, это проверка уже, ну, как бы, вот,
Да. Можно еще вопрос?
Да.
Вот я возьму касательное расслоение
Ага.
многообразие. Возьму первый класс черных.
Да.
Правда, что это всегда получится минус канонический класс?
Ну да, потому что вы должны принцип расщепления, да, применить.
Ну да.
Ну, если вы берете принцип расщепления, то вы просто представьте, что это ваше, не важно это касается, просто если вы берете любое расслоение Е, то первый класс черна это первый класс черна n-той внешней степени, где n это ранг, или r-той внешней степени. Просто а смысл такой, вы берете к Е, можете применить метод расщепления, тогда Е это прямая сумма линейных расслоений.
Да.
Вот, если вы берете ее внешнюю степень, n, максимально, то это просто тензорное произведение вашего расслоения.
Ну да.
Поэтому вы берете C1 от тензорного произведения, это сумма вот этих c. А с другой стороны, вы просто по методу расщепления, это сумма первых классов.
Хорошо. Спасибо.
Да, давайте продолжим. Yeah, so here, so the idea that the recipe is the following. So we define, we change 0 and so of course the problem is that you have in your homology and cohomology. So you have ice homology, that ends at 0, yeah, and you have ice cohomology that also ends on 0. So yeah, so you want to write down the following. So you first of all you want to change the order such that your sequence will be just defined by the sequence of integer numbers. Yeah, so and you change the following objects. So you you define this GA as kernel of n, which is just the kernel of n calculate. Yeah, so notice that the kernel of NA it contains coinvariance. So kernel of NA it contains EG times A, and if and the image of yeah, so image of n it sits of course in the invariance of G. So you may think of kernel on coinvariance. Yeah, so yes, so you the map the kernel in the coinvariance. Yeah, so it contains the EG, so you are thinking of just yeah, so maybe I shall write it just immediately that you are just factoring it by EGA. So it is a subset in coinvariance. Yeah, so subset in coinvariance that comes from the kernel. Yeah, so that kernel of NA, and then so instead of yeah, so instead of M, yeah, so you can think of this as so if here you have a map N, yeah. So instead of this part, you are changing. So you are writing down the subset, which is just kernel of N. Yeah? And then you change A0, H0 functor to get co-kernel of N and in the invariance, yeah, so that just in the set of invariance, which is just yeah, so which is just saying that you are taking NG and factorizing by the image of NA. Yeah? So yeah, so instead of this part, yeah, you are considering inside I, you are considering co-kernel. Yeah, so just the map inside that maps to I0, and then you are applying our factors that are invariance and co-invariance, and you get the cohomology theory. Yeah, so you get the correspond. So we apply here we apply AG. So co-invariance, and here we apply AG, and then you this match your things, and you have the corresponding. So you have the corresponding long exact sequence. Yeah? So by mapping the kernel of NA, it maps to the kernel of NC, we have a long exact sequence. And of course, so the exercise is to prove that it is really a long exact sequence. Yeah, so I mean that I have already written this exact sequence. Yeah, so out of this, so we have matched these two exact sequences by writing down this long exact sequence by the newly defined groups. And of course, so yeah, so we change so here we have so we change for simplicity. We're changing the value. So here you have index. Yeah, so you are putting it -1. So here you have h0.
Снизу или сверху?
Снизу меняется индекс на -1. То есть сначала вы пишете гомология, потом когомология. Но у вас гомология кончается на нулевых гомологиях, а когомология начинается с нулевых. А мы хотим как бы пронумеровать просто целыми числами. Поэтому здесь мы ставим номер -1, тут ставим номер -2 и так далее. То есть когомологию мы не трогаем, а эти сдвигаем. Хорошо?
Просто обычно, когда пишут там вот индекс снизу, это означает как раз минус индекс сверху.
Ну, да, давайте,
Да,
давайте, так сказать, это, знаете, как правило Эйнштейна, да, суммирование, давайте не применять просто для гомологии. Это наличие. То есть вот, ну, как бы вот так получается теперь, ну, и теорема о том, что теперь вот эта вот последовательность точна. То есть вот эти вот как бы, когда вы берете инварианты, факторизуете их по норменным отображениям, ну, у вас также все равно, поскольку норменное отображение это просто отображение на уровне всего модуля А, то у вас получается, что между вот этими когомологиями у нас есть естественные отображения. So we have natural maps here induced by the norm map and taking invariance, and also here you have natural maps. And only this one is a non-trivial map that comes from the snake lemma and gives you Tate cohomology. Yeah, so what is the reason of introducing Tate cohomology? As I said, so there is a product there is a natural product on Tate cohomology. So there exists a product. Existence of product of cup product Yeah, so the thing is that the main thing about this cup product is the following, that of course it comes from the natural cup product on just now I just for Tate cohomology now let us write down as you wanted, yes, to say now you have positive and negative indices and they are on just I'm writing down them upstairs. So just the product is of course the following. So if you have yeah, so you can form the tensor if you have G modules. Just to say explicitly that you can form the tensor product with diagonal action. Again, there are there could be a priori several actions, but for the group, the most natural one is just diagonal action. And you have the following. You have then you have the map from HP X G. And what is main property is consistency. That is consistent consistent with a coboundary map. With a coboundary so that means that suppose, so assume that you have exact sequence so such that if you tensor it by B, it is also exact. Yeah, so of course this is, I mean, as you can see, this is, ну, то есть это требование, so this is the claim. So then you can just, you have the corresponding for any A. But notice that this is more claim about the Billion groups than the claim about G modules. Yeah, so that's because the tensor product is always Z. We do not care about G module structure. So somehow it is the claim about the Billion groups. But what you have here, we want to see the consistency. So that for any A and for any B, these two elements of the Tate homology we have, and you have also a coboundary map delta A is HP GA3 to H P plus 1 GA1, and also coboundary map on the tensor product. Yeah, maybe just I'm not the expert in this thing, but maybe it is. One should consider this in the derived setting, so this would be irrelevant. Yes, so that I mean, so that you shouldn't claim that here you have injection. So you have this Tuka boundary map, then you have consistency conditions about the cup product. Then, yeah, so here we denote that this is a cup product. Yeah, so just and then you have delta of a cup product with B is just delta of A B, the cup product of A and B that belongs to H P plus Q plus 1 G A1B. So this yeah. So why this is yeah. So I want to prove the existence of this map. This is somehow yeah. So you can first look at MacLean book where you have so there is a way to yeah. So if you have the X functors, yes. So then you can just X functors are represented as resolutions, yes, so that not by resolutions, but by exact sequence between the modules, yes, so something like this, up to the ordering, there is A, etc., B that ends in B, and you can think of resolution. So exact sequence starting at B and ending in C. And X allows, so you can take a product by just getting rid of B and composing it into the longer resolution. Yeah? So this is one of the way to do it. And there is similar but less well-known construction about the Tor functor. As so this is somehow so this is represented as a complex where one of the errors is reversed. So you may look at it at MacLean book. It is not complicated, but it somehow just requires time. And also there is a similar way to compose Tor and X functor via this composing this complex for X, this and the corresponding complex for Tor functor. Maybe next time I could comment about this. And then you have, in general, you have this kind of product for cohomology. However, so here you have the only thing is the following, so that so when you are speaking about the shift, so why why this in order to speak about this shift we really need Tate cohomology, because when this was precisely your question when we are so how did we use this kind of shift, yes, of the visage, yes, so we have put A into co-induced module, yeah? And then you take a quotient, and we were able to reduce cohomology with higher index or homology, yes, by delta map with homology of the small index, yeah? But of different module, L tilde times A. And you may introduce and notice that so for co-induced modules Of course, if you take zero cohomology, the zero cohomology will be non-trivial. But for Tate cohomology, zero cohomology of co-induced module is everywhere trivial. So this means, so for co-induced module, so exercise module. Now we have trivial Tate cohomology everywhere, and this implies, yes, so for finite G. Yeah, so just so this tells you that that if you want to take a product, so if you want to calculate a product, a cup product of AB, yeah, so A lives in the index I and B lives in the index J, you may, so you search for the target, yeah, so just AB should be in the index I plus J, yeah? So I plus J. But then you can simultaneously, so by having this shift delta, you can do it in a way that you can move your module. So one of the elements can be moved to 0. Yeah? So this means that when you are moving to 0, so I is changed to I tilde equal to I minus I. J is changed to J tilde to J minus I, and just I plus J is changed to just I plus J is changed to I minus J. Yeah? Via just if you introduce the shift of degrees. Yeah? So so it shifts to J minus I. So when you apply this co-bound, so you may do the following. So you may apply co-boundary map that I will be 0. So I tilde is just 0. So the target, so here you have A that lives in invariance, B, so you have some chain. So you have some chain in J tilde corresponding to the module B. And you simply can map, so if you take chain, any chain, and multiply it by invariant chain, you also get a chain. So you also by multiple, so this lives in the degree 0. So if you look at B, you have B, which is cochain, and for invariant you can simply do everything. You just I mean whatever operation you do, it doesn't change the cochain. Yeah, so that then you can map it to A times B. So this is also cochain. Just because for the following reason, for example, we can take non-alternating, so homogeneous cochains for simplicity. Yeah, so this is homogeneous cochain, and so this are I plus 1 terms, and when you multiply this homogeneous cochain by invariant, it is clear. Yeah, so this is B. Yeah, so that B is applied to G1 GK. It is also, so you have the condition of being homogeneous, So the only thing that you should check is first keeping homogeneity, because this is G times B, G1, Gk. But for invariant, it is clear that you can plug in invariant here. Yeah, so just multiply by invariant this function, and this won't. So we'll keep the chain invariant. And differential, of course, when you why it is convenient to take invariant preserves homogeneity. Because simply because if you if you write down the same for, so let me write it down anyway explicitly. So this is just saying that you apply G to AB, where you multiply them, but G is invariant, so this is simply A applied to B, GB, G1, Gk. So that's why it is the invariant doesn't spoil anything. Yes, so this is G of A times G of B, and as the element, and no, just as the thing is in B module. Yeah, so by this chain we construct, of course, the chain and the values which is a tensor product. Yeah, so and differential looks like the following. You just get rid of the elements in homogeneous chains. The differential of your cochain d of d of b applied to g1 gn plus 1, you are increasing the number of entries. It is simply just applying b to the smaller, so 1 minus 1 the degree I. Yes, so you are just getting rid of some GIs here. Yeah, in your chain, and of course it commutes with multiplying by A. So you see that so this gives you the way to define uniquely. So if you have this consistency, so whenever, so if you have Tate cohomology and you have a claim that you should have this kind of consistency, this tells you that you can shift by delta to any place you like. For example, this can be shifted to invariance, this is also shifted to the corresponding invariance. And here I have made the shift also for B. So for B, I do not need the shift due to this formula. Yeah. So this is only shift for I, and the target is just J. Yeah. So the target is shifted, and only one entry is shifted. Yeah, via because of the linearity of the product. And so you see that by this observation, yes, so multiplication by invariant is unique operation. So you cannot imagine anything else on the product. So yeah, so and of course, yes, so you should say that on the set of invariants, you just define it as a multiplication, and this allows you to define it on all the chains. So and that is a benefit of Tate cohomology. That's why they are more important for us than other type. Yeah. Also, yeah. So there is so we use the tensor product. Yeah. So but there is also yeah, so there is also a just an interior product that can be introduced. Interior product. Suppose that you have a map from phi a times b to c, which is G equivalent by linear map. By linear. Yeah, so meaning equivalence means, of course, that if you want to apply S to the argument, it is equal to applying S to the phi of AB. Yeah, so the map between the map between invariants, of course, defines the map between G times BG to CG. Yeah, so the two invariants map to, if you restrict phi to the set of invariant elements, so they will map to invariant elements due to the equivalence. Then this allows you to define as a composition a product. Yeah? So allows to define product. Again, by means of the formula given above. Yeah? So just on tate cohomology. So by means of the argument. And of course, yes, so I want to have again just AB is so if you just have if A is equal to a delta of A tilde, yeah, so I want to write this down as a product, a delta of A tilde of B, which is equal to delta of A tilde B. So about this shift. And why we need this type of product? We shall need this for applications for just this. We shall so why we need this kind of products? We will define our reciprocity maps by so that will be from the Galois group modulo its commutant. It is the first. So let us recall that what we have so far. We have proved that first homology is just G modulo its commutant. Yeah? Then, if you have some kind of class, for example, 2 class. Then you can map, also, if you have some and this is homology. So far we have calculated homology of Z. Yeah, so H1 H minus 1 G Z. Yeah, so was just G mod commutant. And we want to map it, actually, this guy, we want to map it to the multiplicative group of the field, modulo the norm group. So the multiplicative group K star modulo the norm map applied to the initial field. So multiplicative group of K star is just what? It is just invariance of, as we have noticed, of Galois group. So G is always the Galois group of L over K. Yeah? And this is precisely norm map. So the norm map applied to L, so this is an image of the norm map. So this simply, this guy is just H0 of G. So by Tate, yeah, so of G L. Yeah. So
Place L, L cross
да. Мгм.
everywhere.
Да.
And,
Да, и тут, конечно. Да. Ага. Ну, да, я хочу в мультипликативную группу. And so the claim that we are going to prove is that this is just cup product in terms of Tate cohomology. So this is cup product with some class, with some fixed class that we will specify. And that's why these things are quite important. All right. So this yeah. So this tells you the following. Yeah. So yes. Also, we want to discuss. Yeah. So notice that we have proved before. So we observed the following proposition that tells you that if yeah. So suppose you have G is written as a two coprime factors. Just MP is equal to 1. So GP is a seal of subgroup. So far we have proved the following, that if you want to look at the class, so you can consider, yeah, so you also can consider the restriction in terms of Tate cohomology, not only on Galar cohomology. The changes are minor only in the first and in two places. So you may consider so here you have elements that are annihilated by the order of the group, by GP PS, and this tells you that if you look at p-torsion part, so we have proved that if you take p-torsion part, you have inclusion. So p-torsion part. Yeah, so this is inclusion. So if you want to define the elements of the group of finite order, yeah, so you see that you can simply restrict them to Sylow subgroups, and notice that we have many Sylow subgroups because we have introduced the so-called decomposition groups. And so just yeah, so it is far from the end, but just I'm a little bit tired. Just ничего, если мы сейчас закончим. Ну, просто я что-то не очень хорошо чувствую себя, поэтому вот. Ну, в общем, как бы все, давайте я, так сказать, прорекламирую в следующий раз, что будет. Но это, ну, хотя, не, я вот сейчас, давайте 5 минут сделаем перерыв, вот, я отдохну немножко и продолжим. Вот, давайте так. Вот. Да. Пока понятно, да. Стоит прокомментировать проспаривание Тора и Эрса в следующий раз? Ну давайте так скажем. Это недолго, просто нужно посмотреть. В принципе, там как бы вот, ну, классические вообще эти формулы, они на самом деле, ну, вот можно их вот так делать, ну, как прописано. Классические все-таки, ну, как в топологии, да, произведение уподобия, ну, на симплициальных концептах, да, ну, как вы берете, ну, у вас есть концепт, который принимает значение на симплексе, вы формируете из двух симплексов, да, их, ну, соединяете два симплекса по одной вершине и применяете к нему концепт, да? То есть в прямом произведении вы отмечаете в одном симплексе одну вершину в другом, и вы должны подставить одно и то же значение. Ну, вот, первого концепта, второго. Вот. И как бы, ну, это я имею в виду, когда вы берете внутреннее произведение. Вот. Ну, как бы тут тоже можно, в принципе, если хочется, использовать, ну, исходную формулу для цепей. Ну, то есть, как бы, это вот обычно, ну, это написано в книжке Эленберга Маклейна. Или сейчас, да, наверное, Эленберг Маклейна. Нет, это вроде вот, да. О, в смысле, Эленберг Маклейн это пространство, нет, в смысле, это в книжке Картана есть. Есть еще книжка Картана по гомологической алгебре, там вот вроде как эти, ну, формула прописана.
Не, ну это просто как бы произведение экспов.
Ну, не совсем, это тут,
Ну, для вот
ну, и таров с экстами, то есть это спаривание таров с экстами и произведение экспов. То есть тут как бы, при том, что, смотрите, у вас же, ну, тут как бы вся идея в том, в согласованности вот с этим граничным отображением. Ну, то есть, как бы, что вы не можете, так сказать, как написать произведение, но все-таки, ну, а то, что вы получаете, гораздо лучше.
Нет, ну, если вот мы забудем про центральное граничное отображение, которое...
Нет, тут как раз вот центральное, оно самое важное, потому что вы ваше произведение можете сдвинуть так, чтобы одна компонента попала в кодировку 0, за счет этого вторая просто умножается на инвариант. И вам очевидно, что коцепт умножается на инвариант, вы получаете коцепт. И... А?
Ну,
в смысле, вот, ну, как бы мы с вами так говорим.
Ну да.
Вот.
Не, ну просто вообще исты тоже, они же естественно умножаются.
Но они как раз и умножаются, да, вот,
Если
они
мы-
согласованы со сдвигами, да, ну, то есть, как бы,
Ну, да.
если подумать.
Если с точки зрения производной категории смотреть, ну, там, сдвинутые хомы умножаются на
Да,
сдвинутые тензорное произведение.
да. Сейчас еще немножко отдохну, спина заболела. Да, ну давайте теперь поизучаем. Ну вот мы видим, что теперь как бы, да, нам важно поизучать, получается, силовские группы. Вот. Но причем вот еще и к тому же покручение, да, если мы интересуемся покручением в ЖА, да, то мы сводим к вопросу покручения в силовской группе. Вот. Но давайте заметим следующее, что если у вас, let us notice that if GP is a P group and it acts so acting on vector space linearly, even the yeah, so linearly on vector space. Over the field of finite characteristics, over P, and then over Q. Yeah, but you can of course consider it over its subfield. Yeah, so then GP has a fixed point. So GP has non-trivial fixed point.
P diverge to Q, right?
Yeah. Q just as P to the power n. Of course, I could say over P. Yeah? Has non-trivial, not equal to 0 fixed vector. Yeah, so this is easy, yeah, just because fixed vectors are, so you can just consider action of this group on the vector space, and it is decomposed into the orbits and orders of the orbits. So GP of V orders is just a GP modular stabilizer of P of V. And this is of course, this is either divisible by P, there is a power of P, P in the power L. Yeah? L of V, or just or it can be just O equal to 1, then V is fixed, yeah? So, and V is fixed. But this implies that if you take the elements from if you take, so the number of elements in V is equal to the just sum of the orders of the orbits. So just GP V is not equal to each other. plus the set of fixed points, the number of fixed vectors. Yeah, so this is just q to the power dimension of v. So this is divisible by p. So this means that the number of fixed vectors is just 0 modulo p. Yeah? So these are numbers that are divisible by p. Then the number of fixed vectors is divisible by p, but 0 is already a fixed vector. So this is a non-trivial element. So this is non-trivial set. So not empty set is divisible by p, and 0 belongs to the fixed vectors. This implies that the set is non-trivial. Yeah, so also we want to introduce the group algebra. So I want to understand, we want to take the group algebra of our group G over, so let me say that K is just FQ. So we can consider the group algebra here, and you can consider evaluation ideal. So just augmentation ideal. And you see that it is maximal simply because it is maximal because the result of the so it is two-sided maximal ideal because the quotient is just k, two-sided, just because by definition it gives you, so this is a kernel of this p. Yeah? And notice that so exercise that it is the only maximum ideal. Yeah, and the reason is the following. So maximal ideals comes from representations. Yeah, so that you can just you can consider radical of K of GP. And radical is just the intersection of annihilators of M, where M is a right GP K of GP modules. So the intersection of the annihilator. But notice that here M is simple, so simple. So it doesn't contain smaller submodules. Yeah? So this is definition of radical. And notice that there is since you have the property that GP on any vector V has a fixed point, so this implies that you have only one irreducible module, which is K. K is the only simple K of G module. And annihilators of irreducible representations are maximal ideals, two-sided maximal ideals. So actually, you see that there is only this radical is just and the IP is precisely annihilator of K. So just IP can be identified with the annihilator of M of this one-dimensional module. So this implies that radical of K of GP is equal to annihilator, is equal to this augmentation ideal. Yeah, so notice that, just exercise, just prove directly that I is nilpotent. So I is nilpotent ideal. Yeah, so meaning, so there are few notions of nilpotent ideals. So in non-commutative algebra, so for example, you can ask about the following property that it consists of nilpotent elements. Yeah. So that means that any element of this ideal is nilpotent. But if you, from the viewpoint of nilpotence for ideals, you should consider the power of I, the big power, meaning that whenever you take any elements In from this I, and you take sufficiently large product, then this is zero. So, and here for finite dimensional algebras, this is surprising. So this is non-trivial theorem. I mean, it's not too complicated, but if you try to prove it, it's, I mean, you should be clever. So there are some kind of reduction steps that are not completely evident, and you may easily just work out it in a different order, so you will, you can be mistaken here. And but anyway, so there is a theorem that says that for finite dimensional algebras, nilpotence of any element implies that the ideal is nil ideal. Yeah, so and of course you cannot change this, for example, by saying that your ideal is generated by the set of nilpotent elements, because you have matrices. And matrices can be generated by upper triangular, strictly upper triangular matrices and strictly lower triangular matrices. If you take them together, well, you will get the whole matrix algebra. So this is more or less precise statement. And here the situation is a little bit easier, yeah, because this ideal is, I mean, you know the generators, for example. So if you haven't seen the proof of the theorem for finite dimensional algebra, so that it is interesting to prove this. But and also, yeah, so one can prove that separately that radical in finite dimensional algebra is nilpotent ideal. Yeah, so that's why I mean that's why a posteriori you know that the radical is. So actually it is a maximal nilpotent idea in your algebra, maximal nilpotent two-sided idea. So this tells you, yeah, you have also for this thing you have also Nakayama lemma. So in a non-commutative setting. So Nakayama lemma. well, if your M is finitely generated module, and M is equal to radical of A. A is a ring, yeah, so of M. A is non-commutative. Then M is equal to 0. So application of this thing is a characterization of the module to be 0. Yeah, so just lemma G is a P group. A is as a module is a G module with rather strict properties such that P times A equal to 0. It's not only P torsion, it is just P torsion in the strongest sense. Yes, so just then the following is equivalent. Are equivalent statements. Yeah, so this is characterization of the module to be 0. A is equal to 0. You are calculating H0 cohomology. So this is not state, this is ordinary homology. So invariants are 0 and co-invariants are 0. Yeah, so maybe it is now I would like to stop for today. So next time we shall discuss several characterizations of the modules to be 0 or non-zero with the conditions of having torsion and not having torsion. Then we shall discuss the homological conditions of the module to be free. We also have such a homological condition, and as a final result, we shall have a lemma that will give us the following. It will give you criterion of the product. So suppose you have a fixed element and you want to check that the cup product with this fixed element is isomorphism. So there is a homological criterions via reductions to the Sylow subgroups that allows us to check that this map is isomorphism, and that is the main. So that is the main lemma in class field theory, local class field theory. It is called the Tate-Nakayama lemma. It is rather dull and technical, but in the end of the day, you get the proof that multiplication by some special class gives you isomorphism, which is quite important for us. And that will give you class field theory. And historically, there were some people were writing down different formulas that were quite complicated. And they were, so you may see that if you look at even at multiplication by the class co-boundary maps, because you have Tate cohomology, they are quite involved, yeah, because there are norms that are involved there, etc. And the main simplification that was in the beginning of our century, of the previous one, yeah, that people has observed that class field theory, this abstract formulas has something to do with Galois homology, and can be written just in a unifying way. So as the classes, I mean from the viewpoint of cohomology and multiplication of the classes, all formulas are more or less straightforward. However, there are several compositions that you have to take in different directions, which gives you a non-trivial path in this.